model spread, and two of the most popular issues are, one is aerosol-cloud interactions, the other is cloud feedback. And this is from IPCC AR5 that shows ERF ACI in AR4 is this range, and AR5 is this range, which is really not reduced. AR6 is also a very large uncertainty range in terms of ACI. So let's just agree that ACI has a large uncertainty range. So why is ACI important? So my training is mostly from Phil Rash. He was my postdoc mentor and my boss for many, many years. So he introduced me to this idea, this concept that because aerosol forcing was found to be well correlated with the total anthropogenic forcing, and that was very well correlated with climate sensitivity. That was first found in this paper by in 2007. And they also have a follow-up paper to demonstrate that this is true for CMIP5 models as well. And the newer paper that says, well, we still find that the ERF, aerosol ERF is still has a good correlation with equilibrium climate sensitivity. But then in CMIP6, things start to change, that you don't really see a correlation between the two, and then you also don't see this, the science actually also negative. I think Andrew once told me that we shouldn't really draw a line here because there's really no correlation, right? It's pretty scattered. So there's something new to be learned in the new set of models, which I'm not gonna talk about today. I'm just putting all these unknown issues and puzzles to be solved later. This is another puzzle that I don't understand. The aerosol ERF seems not to be the only thing to consider in the climate sensitivity. So this is the E3SM model. In version 1 and version 2, the red and blue lines here, and you can see that this model suffered from this significant cooling in the mid-20th century, and then followed by a rapid warming. So this is attributed to overly strong aerosol cooling effect in our model, in the DOE model. But then one thing I always find it puzzling is that the CSM has very similar aerosol ERF, and yet the CSM doesn't have that same cooling behavior in the mid-20th century. So there must be something else going on that I think we should all investigate. And this is another nice paper that I wrote, I didn't write, that I read. I found it really interesting. This is the UK ESM, and comparing the blue line and the red line, they made several minor improvements, which I don't think that's really, well, from the description, I don't really see how that could change ERF ACI, which they didn't. The aerosol ERF is roughly the same. But then you can see that one model produced this rapid cooling, the other doesn't, right? And so this is one interesting thing that I noticed in this paper. And another interesting thing is that if you do the climate projection, then the two models basically produce a very similar climate projection. So whether or not you reproduce the 20th century temperature evolution doesn't really impact your climate projection. So this is another thing that's counterintuitive and that I don't understand. So I think these are interesting issues to investigate later, and it's not going to be in this talk. So in this talk, I'm only going to talk about how aerosol and aerosol-cloud interactions are represented in the Earth system model and how we try to improve them. So just one thing, first thing to mention is that there are several common challenges that we face. One is limited knowledge about the background or natural aerosol and the droplet number concentration. So this is first well documented by Ken Koslow's group, and they found that they did this perturbed parameter ensemble and found that 45% of the variance of aerosol forcing comes from the perturbation in the natural aerosol state. And they found that this result points to the importance of understanding pristine pre-industrial-like environments with natural aerosol only, right? And then, of course, the reason why that is important is because let's focus on this plot. The cloud albedo versus cloud droplet number concentration is not a linear relationship. And it's, if you if your pre-industrial state simulated by your model is right here, and you have the same anthropogenic aerosol force perturbation here, then you turned out to have a very large change in cloud albedo. But if your base unperturbed state is here, and then you apply the same aerosol perturbation, then you have very little cloud albedo change. So that's why the base state really matters. And this is another paper that demonstrates that from observations, the relationship between droplet number concentration and aerosol index is not linear, it's a sigmoid relationship. So this has been emphasized multiple times. But we don't have enough knowledge about pre-industrial conditions because we don't have observations back in 1850 or 1750. But there's a very good way to estimate that, which is to use the Southern Ocean as a proxy. So this is a nice paper by Isabel McCoy. She found that the droplet number concentration in the Southern Ocean observed by satellites is significantly higher than the models, the current state-of-the-art climate models, by a factor of 2, right? So this a very large difference here. And then she also found that if you calculate the difference, the interhemispheric difference of droplet number, then calculate the droplet number difference between present day and pre-industrial simulations, they have this very nice relationship, which means that you can actually use the northern and southern hemisphere droplet number difference as a constraint for your PDPI difference. So that's another very good constraint on the aerosol effects. So one thing to emphasize here is that I think it's now established that the climate models seem to underestimate the droplet number or background aerosol number concentration in the pristine, clean environment. And common challenge number 2 is that we seem to have overly strong cloud albedo effect. The Toomey effect in the model is very strong. You see that this is the joint histogram of CDNCE versus CCN. From E3SM, this relationship is really tight and the slope is near 1-to-1. From observations, you see this is more scattered and the slope is less than 1, right? So this means that in the model, we seem to have a greater Toomey effect, and that's driven by stronger and tighter relationship between CCN and droplet number concentration. But what does it tell us about the model deficiency? I think maybe it's related to our treatments in aerosol activation, or the other thing to mention is maybe the complex climate system in the real world has other factors, other mechanisms that's going on, but in our model, there's only aerosol activation that's controlling this relationship. And so the buffering effects is really not in the model. So that's one hypothesis. Common challenge number 3 is lifetime effect also seems to be too large. This is the susceptibility of precipitation probability from observations and from the model estimates. So it looks like when you increase in resolution, you are bringing the model estimate to be in better agreement with the observations, but we're still seeing a very large gap here. And that also might point to the model deficiency in warm-rain processes and cloud adjustments, which we have warm-rain process representation in the model, but we don't have cloud adjustment process in the model. And the challenge number 4 is that do we really know what the truth is? There's really not many observational constraints that can be used for this aerosol cloud interactions. So satellite observations have the global coverage, but they are subject to retrieval uncertainties and limitations and sampling limitations as well. Field campaign or ground-based measurements have limited coverage in space and time. And most observations we have are only good for evaluating the model's state variables, but they are not able to tell us where in the model which mechanism is wrong. And so there has been a lot of efforts on process-oriented diagnostics, and they have been developed. So this is one of them by Ed Greispier. So he was finding that if you use this joint histogram and to find this inverted V shape to describe how liquid path will respond to the perturbation in droplet number. And this positive slope part represents the precipitation suppression effect, and this latter negative slope part represents the entrainment or evaporation or other adjustment processes. Although these are not represented in climate models, but perhaps the model has a way to manifest itself to mimic that behavior. We don't know. So here's what our project is about. This is enabling aerosol cloud interactions at global convection permitting scales, or EGOs. Our goal is to achieve unprecedented realism in predictions of the role of aerosol and aerosol cloud interactions in the Earth system through the combination of advancing fundamental science and utilizing model data science and computational methods to address critical challenges facing the nation and DOS. Now, it sounds like a really awesome project, right? So that tuition is paid off. And this is our a simulation that is a coarse resolution simulation. That's a 1 degree model's results, and the orange is aerosol and white is cloud. So we can immediately notice several deficiencies in the model. That first, that the model resolution is really coarse, and we have some checkerboard pattern here and here, and then we see a lot of cloud systems passing by, but in terms of background aerosol, we barely notice any background aerosol. The only thing that catches your eye probably is this big aerosol plume out of Asia and nothing else, but we know aerosol is everywhere, right? So this is one issue to address. And then secondly, because of the coarse resolution, we see that this 100 kilometer grid box that contains both cloud and aerosols, but we know from high resolution modeling that aerosol plumes and cloud systems are not really in contact with each other a lot of the times. So this is giving us a lot of information here. So let's just also agree that this coarse resolution has highlighted a lot of problems in using this tool to study ACI. So our approach, or the way that we organize our project, is that we will improve the representation of aerosols from its emission, their chemical, physical processes, and to improve the aerosol properties, life cycle, and distribution. And currently, the model treats the sea spray aerosol, mineral dust, wildfire aerosol, biogenic SOA, and anthropogenic sulfate and carbonaceous aerosols. And we will get a better representation of the aerosol composition, hygroscopicity, and optics, and size distribution, and develop a better representation for aerosol optics for radiative effects, and better representation for cloud albedo effects and lifetime effects. And finally, we need to have a modern software infrastructure for exascale computation at global kilometer scales. And then we can use the high resolution model to inform long-term large-scale environment, and use high resolution to inform short-term and small-scale features. And the ongoing effort is to develop this new MEM4XX, which is the MEM4 code written in C++ to achieve global kilometer scale simulation of aerosol and ACI with C++ and COCOS. So this project has 2 national labs and 5 funded university partners and 1 unfunded university partner. So first, I don't like to just go ahead and do the model development and introduce new physics, but I want to first understand our model behavior and where the real deficiency is. So we spend some efforts to build diagnostics. We want to first understand the model and real world features and processes. We collect a lot of measurements of aerosol cloud precipitation meteorology from DOE ARM measurements, and also satellites and other field campaigns. And then we produce a large ensemble of process models and LES to provide those information as well to build a very large data set. Our LES library currently has already produced 200 terabytes of data that's to form the basis for us to evaluate the model and to develop a parameterization. So this is a paper by, 2 papers by our group, Shuai-Qi Tang. He led the effort to develop this ES-MAC diagnostics package that compiled 6 field campaigns in 4 different geographical locations, and that could just, you feed in the model data, it will generate hundreds of analysis and figures for you from aerosol size distribution, composition, vertical profiles, all this seasonal cycle and diurnal cycle and so on and so forth, and those joint histograms as well. And Adam published a paper where it was just accepted a few weeks ago, that he tried to investigate the root cause of the differences in observational estimate, because we know that when we use satellite to calculate the susceptibility and then compare that with the susceptibility estimated from ground-based measurements, they give us different answers. One is higher, one is lower, and the model estimates is right between. So how do you evaluate, how do you constrain your model? And he was able to find that the root cause is the assumption of droplet number retrieval in the satellite, which assumes the constant cloud adiabaticity. But in fact, in model and in real world, cloud adiabaticity ranges a lot from 0.2 to 1.2, right? So when you account for this difference, then we can bring the satellite and the ground-based measurement to similar estimates. So I think that was really, really interesting. And Charlotte just submitted the paper to constrain the warm rain processes using this CFOD analysis that Kenta Suzuki first developed, but we made some updates, and then we demonstrate that we can really calculate this slope from this CFOD and use that slope to constrain the model ERF ACI. So this is just submitted and will appear in ACPD pretty soon. And Laura Fierce led the effort to use particle-resolved aerosol model to compare that with MEM in terms of aerosol size distribution. So the blue line is the MEM size distribution after 20 minutes of simulations, and this is PAR-MC results. So because MEM assumes a fixed standard deviation for the aerosol size distribution, so you can see that we always have a wider spread in terms of aerosol size, and that will have downstream effects on aerosol activation and other things. So this is one structural bias that is current in the MEM model. And this is putting in the aerosol simulator, LiDAR simulator in the COSP2, so right now it's in COSP2, and that, so that we can do apples-to-apples comparisons between the model attenuated backscatter versus the Calypso observations. And Matt Christensen led the effort to assess the aerosol ACI in E3SM using a Lagrangian framework, and then he was able to also find that this nice inverted V shape from our model as well, and that agrees very well with observations. But strangely, one thing he found is that these different lines represents different tunings in auto-conversion scheme, because originally we thought that this shape and the slope should change because you use different auto-conversion, but it doesn't really change that much. So that's one thing that's unexpected. And then when we really try to find a good constraint for ERF ACI for the lifetime effect, we calculate this negative slope here, and then we try to correlate that with our the ERF ACI that we calculated from our E3SM PPE, and we found this very nice relationship that the slope and the PDPI liquid path difference, I mean, this is a ratio, has a really good correlation with the R value of 0.92. So this demonstrates that this is really a good constraint. But there are caveats, and one of them being the sampling needs to be exactly the same, and observations has this liquid path that's within some range that's trustworthy, and the model has a wider range, so you can sample the model the same. It's 4 parameter space, so you have to sample the same way as you sample the observation. So the one caveat, and the other caveat, I will leave that to the end. And lastly, we have this project with my postdoc Yi Qing, that she was looking into the relationship between cloud feedback and aerosol indirect forcing, and we did this perturbed parameter ensemble, and we found that this is very nicely correlated between these two, that when you change something that can change your aerosol cloud interactions, then it simultaneously changes the cloud feedback as well. I think Andrew has some similar results based on CSM as well. So our approach is to establish these liquid cloud testbeds to combine data and model that focus on these four regions that have very different cloud conditions, meteorological conditions, and the three in the northern hemisphere are influenced by anthropogenic aerosols, and the one in the Southern Ocean is a proxy for pre-industrial conditions. So you will think that, well, since the E3SM model has already participated in the diamonds or global 3 kilometer, but of course that simulation doesn't include aerosol. So we put aerosol in, and everything should just run smoothly with 3 kilometer configuration, right? It's all set up. So when I first tried to run it, this is what happened. It crashed, and the complaint caller calculation, no real solution found. And something, I don't know where this is from. Oh, this is from DICOR. DT remap might be too large. And this is from ZM. It doesn't like the convective transport is failing. I don't know where this is. Yeah, just all the fun, right? So, like I was telling Yaga the other day, that originally I asked somebody to do this simulation, and it took them so long that I got really frustrated that how hard could it be? So then they finally get one case work, and they send me their configurations. I thought, well, I would just set up the other cases. I can do this faster. And it took me 2 months to get another case set up. So when you run high-resolution model, there are so many unexpected problems. So that points to the need to have a better software so that we can debug and we can find this issue faster. So we are tasked to pour the MEM code from Fortran to C++. So we first identify all the subroutines that's required from MEM for microphysics and chemistry, all the way to its dry and wet deposition, interaction with aerosols and chemistry, emissions, optics, and everything. And then do the first thing that's called Fortran refactoring, that we break the long subroutines into smaller pieces so that each subroutine only deals with one calculation, right? So that then we do this porting to C++, one at a time. And then finally integrate all the C++ code to this IMXX model, which is the C++ model. And we do this very robust testing in between. And the way we do it is that we take the E3SM output and then feed that into each small units, and then drive the small units to do the calculations, and then make sure the original Fortran and the refactored Fortran produce bit for bit the same answer. And then from Fortran to C++, they should produce very similar round-off differences only, but so far we have only observed the bit for bit behavior also. So it turns out that testing and validation of the code takes majority of the time. You pour the code, that's maybe one afternoon, and then you spend another 2 weeks to make sure that it's done correctly. So finally, we got this 3 kilometer to work, and we are showing this on the left is the 1 degree model, on the right is the high resolution model. And you already start to see a lot of differences in the way that the model simulates cloud systems, and you have a lot of broken clouds here, but here you don't see them. And then another thing to notice is that you see a lot of segregation between aerosol and cloud in high resolution, but in here they are all kind of overlapping with each other. And one thing to mention that I want to emphasize is that the right one looks really pretty, that there are better pictures, but that doesn't mean there are better predictions, right? So that still requires scientific validation. And we do this for all four regions to demonstrate that we now have the capability that can handle different aerosol and meteorology conditions. And maybe if we can wait for 20 seconds for this central US animation to advance a little bit, you will start to see a system, a circulation or a storm is forming in this high resolution model. Yeah, right here, right? You can see the rotation, but then you don't really see that in the low resolution model. So I do think that high resolution model is able to tell you new things
Just for quick clarification, these are nudged runs, right?
These are,
And that's why the storms are sort of matching up?
so these are regional refined mesh runs. We nudge the coarse resolution part, and the 3 kilometer domain is unnudged. Okay. And then we also calculate the ERF-ACI for these 4 regions, comparing the 1 degree model and the 3 kilometer model, right? And then we found that they consistently will accept for Southern Ocean because there's no anthropogenic aerosol influence. And we find that there's a 30% reduction in ERF-ACI. So the E3SM model's ERF-ACI is minus 1.35. And if we reduce 30%, that brings us to the middle of AR6 estimate. I'm not saying it's the right answer, but it's just what it is. And then we do this decomposition analysis, and you can see that they consistently have this reduction. But one thing to notice is that the liquid water path adjustment is expected to be positive, but in this, even in the high resolution model, it's still negative, right? So increasing resolution doesn't really flip your sign in liquid water path adjustment term. Although one can argue that these numbers are also highly uncertain because it's based on regression things. But this is a figure I really like that a very good scientist, young scientist in our team, that she found that in this droplet number concentration versus CCN relationship, this is the observed value. So you can see, as we mentioned before, the slope is really flat. And then we also see that the observation shows higher droplet number concentration all the time. And this blue line is the 1 degree model that has very just a very steep slope, so very tight correlation between ND and CCN, and also demonstrate that the droplet number concentration is biased low. With higher resolution, you now have the similar slope, right? A better agreement with the observations, but it doesn't bridge the gap between, well, in terms of the droplet number concentration. So the model's droplet number concentration is still low, although you improve the slope, right? So at least we solve one problem, just another problem to resolve. So this is the point that I always want to make to our program managers and to the community, that increasing resolution can bring us this far and to help us get rid of those assumptions in the subgroup physics and things like that, and the tighter connections between physics and dynamics and shorter times and everything there is good. But if you don't have those physics, or you have missing mechanisms in there, that's not going to appear magically when you increase resolution. And another set of efforts to improve the aerosol and ACI for next generation E3SM, that's we have a paper on aerosol optics that we use random neural network to replace the old Chebyshev polynomial fit. And we have aerosol activation based on machine learning methods as well. And a bunch of aerosol efforts as well. The postdoc Taufik Hassan led the effort to implement the code so that we can directly read the high resolution 0.1 degree data from the data set, and we also try to make the software flexible enough so we can test the injection height, the sensitivity to injection height or different emission data sets to estimate the emission uncertainty. And Jen Lu led the effort to implement this new wildfire aerosol parameterization to improve the aerosol vertical distribution. Yang Shi led the effort for improving the anthropogenic dust. And I'm going to talk about these two efforts that because we know the low droplet number concentration bias is common and is really important. So we have two efforts to improve the new particle formation process that I will talk about later. And the last one is also very interesting, that the postdoc Yu Yao was leading the effort to implement the giant CCN in the model so that we have one more term to affect the precipitation. So in addition to accretion or convection, we have one more term to form drizzle to affect the warm rain process. So the way the new particle formation mechanisms that we put in is that we first, in addition to the 4 modes treatments, we add one more mode, the nucleation mode, so that's smaller than the Aiken mode. So now the new particle is formed in that nucleation mode. So with the same mass, because the size is smaller, so you have larger numbers. And then when those aerosols grow and become larger, the background aerosol number will be elevated. So that's the first infrastructure that we put in. Kai Zhang led that effort. And Bin Zhao then started this, I think so right now he has 11 new mechanisms to form SOA. And what he found, the take-home message, I think this is really exciting, that this new particle formation generally accounts for more than half of CCN at 0.5% supersaturation over oceans and 15 to 65% over polluted regions. So imagine the default model doesn't have any of those 11. So we're missing at least half of the CCN source in the model, right? And another thing is that the DMS treatment in the E3SM model still uses the old treatments from CAM5 or CSM1, which is basically just these 3 equations that that's represented in terms of DMS chemistry. And this is a new paper that we need 3 dozens of reactions to represent that. And they demonstrate that at least we need to include these 2, because if you don't have these 2, then over Southern Ocean, you are missing more than half of the source, right? Half of the reactions that's consuming DMS. But E3SM only represents these 3. So we had an effort to adopt this method just to see what will it look like. So Raj Mashang at UW and his graduate student Li Tai Kang are leading the effort to compare the default E3SM model, which is this one, and on the left is the observation from Socrates. And this is the droplet number concentration. You can see that the median value is 121 per cc, and the model gives you a factor of 2 lower. With improved the DMS treatment 1 at a time, we are able to see an increase of droplet number that agrees better with observations. However, we just found out maybe just last week, that is probably not due to actually the right reason, because studies have shown that this droplet number and CCN actually should be coming from free troposphere, not the boundary layer. But all the improvements we made is making the boundary layer CCN and aerosol number higher and better agreement with OPS. But the free troposphere, the increase of this CCN and the aerosol number in the free troposphere is still not significant enough. So there are more work to be done here. This is 1 degree and 3 kilometer resolution doesn't give you any new information. So it's very obvious that this is not a resolution problem. This is a mechanism problem here. And this is the aerosol activation work that we show that this is a comparison between the partial model truth and the Abdul-Razik and GAN parameterization used in CAM and E3SM. You can see that the parameterization is really not doing a good job, but with the neural network, we are seeing a much better agreement. And the result is that it increases the aerosol activation and droplet number concentrations increases a lot in the model. And then this is an effort to better simulate the droplet collision columns in the turbulent environment. So Kobe Spant is leading the effort that uses beam microphysics and then perturb all kinds of parameters and observe the droplet size distribution from our measurements. So we collect 50,000 of them from 4 different field campaigns, and then feed them into this collision column solver to compute the evolution of DSD. And then Andrew Geis is doing this machine learning emulator development work. This Yu Yao did this giant CCN effect using ERF ACI, so that reduces ERF ACI. And this original model shows basically no relationship between the surface rain flux and the coarse mode aerosol number concentration. And when we implement after we implement the giant CCN effect, so now this blue line shows that this relationship starts to appear. This is a net effect. Not sure how we can constrain this, but this is showing that the model is at least sensitive to this treatment. So the next step, of course, is to represent this and then maybe use LES to constrain those effects, because right now there's a lot of assumptions building in there, like the size of the GCCN or the size of the drizzles that it forms, things like that. And this is a figure showing this other effort to improve the aerosol optics. That right now, the model uses the Gann and Zafari 2007 aerosol optics that based on me calculation and use Chebyshev polynomials to feed that lookup table. So we first generate a new table that's at higher resolution, and then we build a neural network to feed that. And the neural network was originally very expensive, so then we use random search algorithm to drop the neurons that's not contributing to the root mean square error. And so that significantly reduced the computational cost. So this is the parameterization versus the me calculation, the truth. And the gray area is the original parameterizations. So you can see that they really have some problems with short wave extinction when the extinction is large. And it has also a bias here. The red contour here bounded the predictions from the neural network. So you can see that this is at least 2 to 3 orders of magnitude improvement in terms of mean absolute error. And this success actually just laid the groundwork for the machine learning emulation of shear core optics. So we already built another parameterization that uses the shear core optics so that we can improve the BC black carbon absorption. And also, we are working on this new BC optics, black carbon optics, that accounts for the complex morphology of the black carbon. So we can finally step away from internal mixing assumption and do some more complicated aerosol optics. So summary is that the new software really enables the kilometer scale simulations on GPUs, and that opens doors for exciting science and actionable predictions. Of course, this is a lawyer speaking again. Regarding the common challenge number 1, coarse model resolution, so we're building this next generation ethereum that can do this kilometer scale simulation with aerosol ACI. We find that the increasing resolution produces better pictures that look more realistic, but quantitative analysis indicates that they improve some aspects of the simulation, but not others. Missing mechanisms do not emerge in kilometer scale simulations. Low background aerosol problem is alleviated by our new nucleation mode aerosol, new particle formation mechanisms for sulfate and organics and DMS chemistry, machine learning activation, and these things, they are all very important. The overly strong Toomey effect problem that we try to improve the droplet correlance process. Increased resolution did help in terms of the droplet ND and CCN relationship. And the lifetime effect might be connected to precipitation. I think this is a very challenging. So in high resolution, we find the liquid path adjustment is reduced, but still negative. So that means our fundamental representation in the physics is still not correct. And positive aerosol direct effect, I didn't mention this, but it was a bias in the model. And that's likely due to overly strong black carbon absorption. So this new aerosol optics will provide better accurate results. Finally, those process-oriented constraints are developed, but I'm going to show you one thing that they need more work to work in the kilometer scale. So this is this. So this is the 1 degree inverted V shape. When we put the same data, observational data, in the 3-kilometer grid, they now show multiple modes. right? And I mean, scientists have say that this is precipitation suppression, this is entrainment, evaporation adjustments, and I don't know what we will do with this. So we need to do some more analysis to understand these modes, and then we can start to see if we can use this to evaluate and constrain our 3-kilometer model. And our next step is to do a lot of those kilometer scale simulations, evaluation, analysis. That's a ton of heavy lifting work. And then because we only just poured the software and we didn't try to improve them in the meantime, so all the improvement, all the new physics that we developed is still on the Fortran code base, right? And so then we went, then take the next step is to merge them and improve the physics and improve the algorithm and things like that. And then we think that we need a better treatment for chemistry, natural aerosol, and SOA. They are very expensive, so they cannot be used in a climate simulation, but can we find a way to parameterize them so that we can mimic the behavior, but not doing the full explicit calculation? So that's an ongoing research. And better represent the subgrid variability and cloud adjustment based on LES and process model, and develop diagnostic scales, the kilometer scale diagnostics. Finally, so far we have only touched aerosol impacts on liquid clouds, but what about their interaction with ice, mixed phase, convective clouds? There are a lot of other things that we haven't studied. And because I mentioned this LES, I also want to shout out this Pinnacles model that we developed under this project originally, but then it was now used in multiple other programs as well. It's called Pinnacles, developed mainly by Kyle Presso and Colleen Carr. This is a new LES model that is written in Python and can be connected with Fortran physics parameterizations. It runs very fast and it runs on GPUs as well, and very efficient code. So we can use this model to generate a lot of data on DOE machines. So Colleen is preparing the manuscript to document the model and the data will be made available to the community to do all kinds of fun research. So this cannot be done without a huge, fantastic team. So we have a lot of people from these different institutions, and I think I don't have time to name their names, but this is just to recognize everybody's contribution to this effort. So thank you.
We have some time to cross-examine.
So you talk about the horizontal resolution, but I think especially for shallow cloud, the vertical resolution is also important. Are you planning to look into that as well?
We have two configurations. One uses 64 levels, the other uses 128 levels. And I think there's some studies that shows that the model is even more sensitive to vertical resolution than horizontal resolution when your horizontal resolution is high enough, right? And that's just another Pandora box we're so afraid.
Well, yeah, if you think about stratocumulus, for example, which we know how important it is for the radiation budget, resolution near the inversion is critical. I mean, we know that from LES studies. I don't think, for example, entrainment rate is still kind of well handled, even at very high resolution. So, yeah, I think this is something definitely to look into.
Absolutely.
Great talk. Lots of work there. I was glad it was on the further work. I was really asking because it was good to see there's an LES being used and trying to understand some of the subgrid. Because I guess at 3 kilometers, it's you're talking about resolving what 15, 20 kilometer regions, and there must be Yeah. Aerosol-cloud interactions, it's so important, the covariance of the different things involved, the aerosol concentration or the microphysics or the water vapor really matters. Can you maybe speculate on how you begin to represent that at those higher resolutions and maybe some of the biases you've got? Do you think that could really be solved by representing the sort of missing covariance of those features?
So that's why we have this LES component in our project, which is that we think that the 3 kilometers is not a high enough resolution to represent those covariance and this covariabilities of aerosol and clouds. And so we did those LES with standard aerosol forcing, and then we doubling or halving the aerosol perturbations to then let the model to produce all the clouds information. And then LES is coupled with the beam microphysics to produce all these results. So, and we just started to analyze that, and we find that the model is not capturing those updraft and downdrafts pretty well, very well, and then the updraft, the vertical velocity at 3 kilometers, where subgrid variability of the vertical velocity is still pretty large. So these things needs to be implemented in the, find a way to influence our turbulence parameterization and how that will connect with the aerosol activation. So there's a different efforts that try to understand how we represent the aerosol activation, accounting for the subgrid variability of updraft and aerosol concentration and relative humidity in there.
Just to interpret what you said, I think you're saying that the first thing is to try and get the dynamics a little bit better, and then you can worry about the aerosol cloud interactions.
Did I say that?
You're the lawyer.
This is being recorded, so, okay.
Hello. Thanks for the talk. A lot of work, very hard work, right? So before talking about aerosol and cloud interactions, from the weather forecasting perspective, it is really challenging to simulate the cloud, fraction and location in the right place, right? So how do you verify, if you guys actually simulated the cloud, the right location and fraction, in your simulation?
Yeah, so that's something that one of my team members who are responsible for doing the 3 kilometer resolution run, evaluation of that 3 kilometer run, came to complain that that she didn't get enough samples because the clouds are not forming the same places, the aircraft measurements, right? And so what we did was, well, there are multiple ways that you can do that, which is just to take that nearby, the samples that's nearby, and or you can use dynamical regimes to just select the clouds that's under the same meteorological regimes and do the analysis there. Or you can just do a statistical analysis rather than point-by-point analysis. Yeah, I guess there's no perfect way to do that.
Okay.
Okay, thanks. Great talk. I learned a lot. I'm curious if you've looked at, so there's some observational studies that have shown that at 0.2% supersaturation, the CCN population can actually dominate by sea salt. And this is the case down towards Antarctica. And this is where I think observations can really help us in determining whether a model is getting the right process right. The other way we could do it is also looking at seasonal variability. And I'm just curious your thoughts on that, how you can really know if your model is getting the right answer for the right reason. And then the other question I have is related to John's, which is there any effort to determine if the model is representing supersaturations correctly? Because the CCN activation is, of course, very sensitive. There are some aircraft measurements of supersaturation of vertical velocity, and so I'm just curious if that's something that's been able to be incorporated in Eagles. Thanks.
Yeah, I remember seeing something about supersaturation in our proposal. Anyway, so to answer, I guess I have a better answer for the first question. I think the literature suggests that the austral winter time, the CCN is dominated by surface, the sea salts, sea spray aerosols. But in the summertime, it's dominated by free tropospheric sulfate aerosols, unless we're reading different papers. So that's one thing that what we have been focusing on is to use Socrates to guide us in terms of the DMS chemistry and the free tropospheric aerosol number concentration and CCNs.
Sorry, thanks. I just wanted to say that it's very sensitive to the supersaturation you're looking at. And that's, I think some studies have come out really exciting results of these sulfate particles. But then at the sort of modest supersaturations in these Southern Ocean clouds, I think that there is quite a lot of sea salt still too. So we'll talk more later, but
Yeah,
a place for observations to contribute maybe.
Before we started this new DMS chemistry, or not new, implemented this DMS chemistry that Colette's group developed, Andrew, I think, is a co-author on that paper. We actually tried to just bump up the sea spray aerosol just to see what it did help with the droplet number concentration, but then Raj and the student Li Tai, they don't think that's for the right reason with some analysis. And they convinced me at the time, but I don't remember the reasoning now.
Okay, if there aren't any further questions, thanks again, Po-Lun.
Thank you.
And please join us for cookies and coffee.